Hello, it's Theo, and this is the cart with wheels problem. Okay, so the situation is, we've got a cart with mass m, and it also has 4 wheels, and each wheel has mass m over 4. It is on this kind of ramp thing at a height h, and it's kind of rolling down the ramp, and after it gets to the bottom, it will collide with a spring. We'll get to that part later, but yeah, for now, cart with 4 wheels. And we're also given the moment of inertia of the wheel based on the moment of inertia of a kind of disk. So it's going to be 1/2 ml squared. So in this case, the wheel is defined with radius lowercase r. So 1/2 ml squared. Well, the mass of the wheel is m over 4, and the radius is r, so that will convert to 1/2 lowercase m r squared. So in part A, we're asked to find the total moment of inertia for all wheels. So each wheel is kind of rotating about an axis through its center. So to sum them up, we can pretty much say that they're all exactly equivalent, and we can just multiply the moment of inertia of one wheel by 4. So if we just take this, multiply by 4, we just get 1/2 mr squared for the total moment of inertia. Okay, so for B, we're asked to find the speed of the cart kind of once it reaches the bottom of the ramp and its height is equal to 0. So for this, we can use energy, but we'll take into account rotation. So we'll define that h equals 0 over here, and we'll say the energy at the beginning is at rest, so no kinetic energy, but it does have gravitational potential energy, so that is going to be mgh. But the total mass is not m, it's actually m plus 4 times m over 4, so the total mass is actually 2m, so 2 mgh. And then at the bottom, we have no more gravitational potential energy because the height is 0. Well, I guess if you didn't consider this to be a point mass, it might be something with like the angle of the cart that changes, but we're going to ignore that. So let's talk about the linear energy, linear kinetic energy. That's 1/2 mv squared. But again, the total mass is actually 2m, so we have 1/2 2m v squared, where v is the speed that we're solving for. And then we also have some rotational kinetic energy, which is 1/2 I omega squared. However, the cart itself is not rotating, only the 4 wheels are rotating. So we kind of just got the moment of inertia for the 4 wheels. So we can just do 1/2 times the moment of inertia times omega squared. And then I'll just do a little bit of algebra, just simplify the thing a little bit. So we know that omega is equal to v squared over r squared. So make that change, and then we can cancel out these r's. So we get 2mgh equals mv squared plus 1/4 mv squared, and that is equal to 5/4 mv squared. And from there, we just have to solve for v. So I'll just multiply by 4/5, divide by m, and take the square root. So that's 8/5 gh square root equals v. And that is our speed at the bottom. Okay, so next we are asked to find, assuming the same situation, the compression of this spring. Basically, after it's been on the ground for a little bit, it will run into this spring, and it's going to compress it, and at its maximum compression, the speed is going to be 0, and it'll come to some kind of equilibrium. So basically, we're asked to find the maximum compression relative to the spring's equilibrium. So we could say that x equals 0 right there. Okay, so at the beginning, again, we've got a certain amount of energy. We could form it in terms of kinetic energy, but we know it's equal to the original potential energy of the cart, which we've already found is 2 mgh. So we'll just use that. And then once we've compressed the spring, we have no gravitational potential energy, height is still 0. We have no kinetic energy because we're not moving at all. Or same thing for angular kinetic energy, but we do have spring potential energy. So that's a pretty simple equation. That's what we got. And all we got to do is solve for x. So I'll multiply by 2, divide by hand, take the square root. And yeah, there we go. It's 2 root mgh over k. Again, just algebra and energy equations, kind of for both of these things. Okay, so the last part, D, is you have a setup where the bumper, basically kind of like the board that it collides into before going into the spring. Imagine that has mass, and in a situation where it does have mass, they like measured it or something, and it turns out that the compression was actually a little bit less than the expected compression. And so we're asked to kind of reason that out and say, why might that be? Well, kind of like in word format, you could say like, oh, well, the energy of the cart, it's kind of being used to move both the cart and the bumper forward. And since the bumper has mass, some of that energy is used for the bumper, so they can't go as far. And I'm just gonna, and I think that holds. I'm gonna give like a little numerical example. So let's say the bumper's mass is pretty heavy. Let's say it's like 5m. So we can do a what is it? Not inelastic collision. Basically, we can imagine that the bumper and the cart are sticking together. Yeah, the cart is the bumper's gonna have no rotation, so we can do mass of the cart. Total mass is 2m. V. So initial momentum is going to be momentum of the cart plus this has no momentum, and then final momentum is going to be, it's inelastic, so they have the same velocity, and the total mass is 2m plus 5m. That's 7m v prime. So you can say that v prime is equal to 2/7 v. And then let's just plug this in a little bit and kind of see what energy, because we can say that momentum is conserved, we can't necessarily say that energy is conserved. So I can't use 2mgh anymore. I'm just going to kind of plug this in and see what energy we get. So we've got 1/2, and now our total mass is now going to be 7m. Yeah, total mass is going to be 7m, and then v squared. And then we've still got this 1/2 I omega squared. And we can just kind of plug this in. This is going to go to 4/49, multiplied by 7. It's going to go to 4/7. And this is again going to go to 1/4 mv squared. So this comes out to 2/7. So I have 2/7 mv squared plus 1/4 mv squared. Yeah, I can do the arithmetic, but we're already starting to see this is definitely less energy than this. But yeah, we can just convert it. So I'll multiply by 4/4, so that is 8 plus 7, 28 mv squared. So suppose the bumper mass is 5m, then we get a final energy about 15/28 mv squared, as opposed to 5/4. 5/4 is a little bit over 1. 15/28 is a little bit over 1/2. So we can see our energy would definitely decrease. And if our energy decreased, then this equation was derived from, you can see this final energy must be equal to the initial energy. So if our initial energy is now less, then the final energy must also be less. Therefore, if k is constant, x squared must also be less, so the spring will not compress as much. So yeah, that's about it. Just to review, we found the total moment of inertia for the wheels, which was 1/2 mr squared. We found the speed of the cart and wheels at the bottom, the linear speed, which was square root of 8/5 gh, where h is the starting height. We found the final compression of the spring, given a spring constant, which was 2 root mgh over k. And then finally, we kind of reasoned out why the spring might not compress as much if the bumper that we're colliding with actually had mass. So yeah, that's about it. See ya.